Hello, my name is Olivier Nicole, and I will present you this work about verification of operating system kernels. This is a joint work with Matthieu Lemerre, Sébastien Bardin, and Xavier. In this work we targeted the two worst bugs that can happen in a kernel. The first one is runtime errors. If you have a division by zero, for instance, in your kernel, then the kernel will crash, and it will crash the whole system. We want to avoid that. The second bug we want to avoid is privilege escalation, in which one of the tasks bypasses kernel protections and compromises the whole system. The only way to guarantee the absence of these two kinds of bugs is formal methods. So we would want a verification of these two properties, absence of runtime errors and absence of privilege escalation, that is automated in the sense that we don't want to write a lot of manual annotations. It should be comprehensive in the sense that all the code should be checked, including boot code, including assembly sections, low-level instructions, etc. And it should be end-to-end in the sense that we shouldn't have to trust the compiler. It should be generic, that is independent from the tasks that run on the kernel, and we don't want to have fundamental restrictions on the kind of code that we support. For instance, we want to support unbounded loops that are necessary for priority scheduling. And finally, it should be practical in the sense that it should work on a real-world existing kernels without modification. So we contribute BinSec codecs, a static analyzer to verify absence of privilege escalation and absence of runtime errors on embedded kernels. It performs an abstract interpretation on the system loop to infer the kernel invariants rather than having to write them. And for that we use the fact that absence of privilege escalation is an implicit property, and by that I mean a property that doesn't require a specification. And we perform this verification on the kernel executable, which makes it comprehensive. It is also independent from the applications, what we call a parameterized verification, and to achieve that we use a novel type-based memory analysis. And to make it practical, we introduce a different treatment of boot code and runtime code, and we demonstrate its practicality by verifying an unmodified version of Asterios, which is a real-time industrial kernel, and verifying 96 variants of Educ RTOS, which is a real-time OS developed by our team. So prior work about kernel verification uses different techniques. Two lines of work use either interactive proof or deductive verification. These allow to prove stronger properties than we do, since they prove the compliance to a functional specification, but they also require huge expertise and verification effort. Another line of work, which we call push-button verification, is actually a variant of deductive verification. These methods are more automated and require less manual intervention, but they still require to write the kernel invariants manually, and these invariants can be pretty big. They only support bounded loops, which precludes priority scheduling, and they require a fixed memory layout that depends on the number of tasks, which is an obstacle to genericity. In contrast, we use abstract interpretation to infer all the invariants. We handle unbounded loops and parameterized verification with a low annotation burden. The analysis technique we use is abstract interpretation. It is a technique to automatically infer program invariants, and I will briefly show how it can compute an overapproximation of numeric variables in a simple program. So we analyze binary, but here for clarity I will only show C code. So what we want is the set of possible values of variables at each point of the program. So at this point of the program, I is necessarily 100. At this point, I is 100 and x is 0. And then in the loop, at first nothing changes, and then I is decremented, so at this point I is 99. And now we will iterate again on the loop. So we realize that at this point, in fact, I may be 99 or 100, and we propagate this down the loop, and we will repeat this process until we reach a fixed point, which is in fact an invariant for this loop. And we deduce from that that after the loop, necessarily I is 1 and x is 0, and as a consequence, at the end of the program, I is 1 and x is 42. And these sets of possible values for each variable at each point of the program is an invariant of our program. Abstract interpretation computes correct invariants, and that's why it can prove properties. Here, for instance, we prove that there is no division by 0 in this program. And you may notice that we didn't have to write a specification, so we call this kind of property implicit. And more generally, the absence of runtime errors is an implicit property. So we want to analyze kernels. And what kernels do is, after running some boot code, they alternate between kernel runtime and user code, what we call the system loop. And we want to perform abstract interpretation on that system loop, but the user code is unknown. So what we do is we abstract it by arbitrary sequences of instructions, effectively empowering a potential attacker. But these sequences of instructions are limited by hardware protections, in particular memory protection and privilege level. We will also use the fact that absence of privilege escalation, perhaps surprisingly, is an implicit property. Indeed, if the system satisfies a non-trivial invariant, then it is not vulnerable to privilege escalation. And the proof is quite simple. By contraposition, if there is a possible privilege escalation, then the user code, the empowered attacker, may do anything and reach any state, and therefore the system does not satisfy any invariant except the trivial invariant true. So absence of privilege escalation can be verified without writing a specification. We just have to infer an invariant on the system. I will show how to do it on a very minimal example kernel. So what this kernel does is it saves the context of the task that just got interrupted, then it schedules the next task using a round-robin algorithm and a circular list. It loads memory protection of the new task, and it loads the context of the new task, and then it will give control to the new task. So now suppose that we know everything about task data. We will perform what we call an in-context analysis. So here, for instance, we have two tasks, and initially cur points to the second task at address A7, and CTX contains address A8. So first save context does some memory writes but does not modify the values of these two variables. Then cur is modified and contains A2. Then CTX in turn is modified to contain A3. Then load protection does not modify these variables. And then the user code has control. And the user code can do anything within limits of hardware protections. And assuming that memory protection was properly set up, then kernel memory cannot be modified by the user code, and in particular cur and CTX cannot be modified. So now we will iterate again on this kernel runtime, and we realize that at this point cur and CTX may have two different values, and we will propagate that abstract state down the runtime. And now we have reached a fixed point, which means that this is an invariant of the system. We just found an invariance, so we proved that this kernel is safe from privilege escalation. What this shows is that in-context analysis can verify absence of privilege escalation and absence of runtime errors without any annotations at all. And here I did not detail the set of abstractions that we use to precisely analyze binary code, but we do use a number of abstractions to recover control flow, precisely analyze values and memory, and handle concurrency, and we give details about them in the paper. So this is good, but this method is not generic. We wanted to analyze the kernel independently from the applications, and clearly it's not the case. It's also probably not scalable. For instance, if there are 1,000 tasks, then the analysis would have to enumerate 1,000 addresses. So the key idea here is we need to summarize the memory that contains task data, and we will do it using a type-based abstraction. So here is what our type system looks like. It's similar to C types, but we enrich them with predicates that constrain the values of a type. So here, for instance, this predicate expresses that values of the type flags, when put in a bitwise AND with the privileged bit mask, must result in 0. And each type is given an interpretation as a set of values. So for instance, the interpretation of a pointer type will be a set of addresses, and the interpretation of a numeric type will be a set of values constrained by the predicates on this type. And so the types are typically given by the kernel developers, but the predicates have to be manually added. So there are a form of manual annotations. And this is what our analysis now looks like when using this type-based abstraction. Now all we know is that cur is in the interpretation of the type pointer to task, and that ctx is in the interpretation of the type pointer to context. And in fact, each line of the runtime simply preserves this property. And so does the abstracted user code. So in fact, we have already found a fixed point, and so we have found an invariant on the system, and that invariant does not depend on the number of tasks, nor on specific values of tasks data. So this is a scalable way to find invariants on kernels. A last problem with this approach is that our type-based analysis is good at verifying the preservation of invariants, but sometimes in kernels the boot code establishes some of the invariants, which is quite a different thing. So what we do is we perform a parameterized analysis of the runtime code, and then we perform an in-context analysis of the boot code to check that the state after boot matches the invariant. And this way, we verify the entire kernel. We evaluated the real-life effectiveness of our technique by verifying an unmodified industrial microkernel called Asterios. We verified a port of Asterios for the ARM architecture, consisting in about 10,000 instructions, and the memory protection it uses is page tables. In order to avoid an imprecision in our type-based analysis, we had to assume that all tasks use the same stack size, which is the default, and we analyzed two versions of the kernel. In the first beta version, we found one vulnerability caused by improper sanitization of some user data, and then in a V1 version, where this vulnerability was fixed, we were able to prove absence of privilege escalation and absence of runtime errors in 430 seconds, and we only needed 58 lines of annotations. We then evaluated the genericity of the approach by analyzing a very different OS. Educ RTOS is a small academic OS developed by our team for teaching purposes. It's open source on GitHub. It's both a separation kernel and a real-time OS, and has dynamic thread creation. It's written for the x86 architecture, and is protected by segmentation, and it consists in a bit more than 1,000 instructions. So we proved absence of privilege escalation and absence of runtime errors on 96 variants of EducRTOS, the varying parameters being the compiler used, so GCC or CLang, the optimization flags, the scheduling algorithm, the dynamic thread creation being enabled or disabled, etc. And the verification time ranged from a bit more than a second to 73 seconds, and it only required 14 lines of annotations. Finally, we evaluated the automation and scalability of the technique by verifying a simple variant of EducRTOS with varying numbers of tasks, and we compared the fully automated in-context analysis versus the parameterized analysis, which required 12 lines of annotations. And we found that the time and space complexity of the parameterized analysis is almost linear, whereas the in-context verification is quadratic, which makes it impractical starting from about 1,000 tasks. So to summarize, our tool formally verifies absence of runtime errors and absence of privilege escalation on embedded kernels from the executable with a low annotation burden. And we address existing limitations by allowing parameterized verification and handling unbounded loops, and we infer the kernel invariants rather than merely checking them. And the invariants that we infer can be reused by other verification techniques, so this work can be a key enabler to help automating the verification of more complex systems. Thank you for listening.